This is the introduction to exercise 10.1 on review of probability. I'm going to go through some very, very basic terminology, but stuff you should be able to live and breathe by the end of this week. Okay, so sample space, you should know just a couple of minor things, such as VCAR is very picky, as you are aware. So anytime you're listing sample space, you need to have your curly brackets or your set brackets. Right? An event, union, intersection, etc. You need to know and be very clear in the difference between union and intersection and where they are prevalent. So your union intersection notation as well. You need to know your addition rule of union. So basically to say that the probability of A in unison with B, so where A or B, again you have to keep that in mind, equals to the probability of A plus the probability of B minus the probability of A intersecting with B. Right, so again, I'm not personally aware of what probability skills we're at, so I'm going to cover it at my pace. Let me know if I'm going too quickly or too slowly. Something we need to talk about is mutually exclusive events. There's a massive misconception that mutually exclusive is the same as independent or can be used interchangeably. It is not true. They are very different things. Mutually exclusive events have no outcomes in common. So mutually exclusive events cannot overlap. Whereas independent events, which we'll cover a little bit later as well, just means that one event has no impact on the other. And you can see why a lot of students mix those two definitions up. So mutually exclusive, no overlap. It cannot have outcomes in common, whereas your independent just means that one event or one situation has no impact on the other situation. There can be overlap, it just means that those two won't affect each other. Okay? Alright, so probability in terms of Venn diagrams, Carnot maps, you need to know how to use. I believe you did Carnot maps last year, is that correct? Okay, lovely. We'll just go through some very basic questions super quickly. Find the sample space when 3 coins are tossed with results noted. Every time we're trying to demonstrate a specific set of values or a specific value, we should be using the element, right? It's just a weird E, or you can just draw it as that as well. They both suffice. But the element, sample space where we have heads, 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 tails, and I'm just writing in any order. Heads, tails, heads, tails, heads, heads, tails, tails, heads, heads, tails, 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 and I'm going to close it there. How do we know if we've got the right number of solutions or right number of outcomes in this scenario? Do we have the right number? How do we know? Yeah, because this is a very easy mark to lose. Well, we've got 3 coins tossed. Every time if we toss 1 coin, well, of course, we've got 2 outcomes. If we flip 2 coins, we should have 4, because there's 2 outcomes for each of those 2 outcomes. And if I flip 3 coins, if I have 2 outcomes for each of those 4 outcomes, I should have 8. So I have 1, 2, 3, 4, 5, 6, 7. I'm definitely missing one. We'll add the last one in, which is tails, heads, tails. So just make sure you double check your probability work a couple of times. Alright, hopefully that is quite familiar work for you. Let's move on. In this scenario, we have 500 people questioned and classified according to age and whether or not they regularly use social media. We've got a table here, and this is just pretty much finding probability. Pretty basic stuff. I will fly through this. So one person is selected from these 500. Find the probability that the person regularly uses social media. All I'm doing is identifying, well, if they're regularly using social media, it doesn't say what age, so it's going to be a value of 300. Right? So that's 300 over the 500 with an expected simplification to 3 over 5. It does not specify, so you can write either 3 over 5 or 0.6. You're not rounding, so technically there is no change in value. That's fine. That is an exact value. The person is less than 25 years of age, so less than 25 years of age is going to be this one right here. You would not believe the number of students that get these two mixed up in year 12, so please make sure you double check that. So less than 25 years of age, same idea, 240 over 500, simplifies down to 12 over 25, or 0.48. Pretty easy stuff so far. The person is less than 25 years of age and, so that is an intersection. and does not regularly use social media. In this very specific scenario, I can just identify the specific value associated with this. So less than 25, which is in this column, but also does not regularly use social media is in this row, so therefore it would be the 40 overlap. 40 over 500 simplifies down to 2 over 25, or 0.08. Pretty straightforward stuff. Let's move on. I'll put the notes back up there in a moment if you need to. You need to know how to do probability in reference to your measurement. So for example, in a dartboard with a square of size length 2 meters, we have a quarter circle in a circular disc. We need to find the probability that it hits the blue. So the probability of blue would equal to the value on top being the area, which area of the quarter circle, which is a quarter multiplied by pi r squared. I am again flying through this quite quickly. Please let me know if I'm going too quickly. Divided by the total area, which is just going to be 2 squared, which gives us an answer of pi over 4. Another thing, this is in reference to me looking through the SAC that we've just completed, make sure you remember your units. In this particular case, because a lot of students think of pi as specifically measurement, they would write pi over 4 centimeters squared or something of the sort, and BCO will take off that mark for you. It's probability there shouldn't be centimeters squared. Just give me that heads up. Okay, let's move on. Simone visits the dentist every 6 months for a checkup. The probability that she will need her teeth cleaned is 0.35. The probability that she will need a filling is 0.1. And the probability that she will need both is 0.05. This is your basic year 9 level kind of map / your Venn diagram. I will do both. It says or, I will do both. Okay, so one of the things that a lot of students, again, make mistakes on, this is really basic stuff, but they lose marks on things such as not defining clearly what their variables are. Right? If you just randomly write F and you don't explain it, the examiners can take off marks. So make it clear, let's C equal this, or let's F equal this, etc., etc. In my Venn diagram, of course, don't forget your box. I'm going to label C and F. I'm going to fill in my values. Of course, there's the overlap, or the probability that you will need both is 0.05. I'll fill that in right now. I know that the probability of F, which is 0.1, it should be everything in that circle adds up to 0.1, so that should be 0.05 as well. The probability of everything in C should add up to 0.35, so that would be 0.3. A lot of students stop there. That would be incorrect. Don't forget that, of course, there's a probability that she doesn't need either. Let's move on to our Carnot map. With a Carnot map, it is often a lot easier to just use F and F dash, etc. Don't forget your total rows / columns as well. Wow, that changed color mid-line. There we go. All right, so we're going to fill in the same thing. It will give you the same information, right? And very rarely will the examiners ask you to do both. Okay, so it just makes it easier to do one or the other. Be familiar with both though. 0.05, 0.05, 0.3, 0.35, because we're just adding them up. It's basically like a really simple Sudoku. And these should be our answers here. Am I going too quickly? Okay. I'm going too slowly. What is the probability that she will not need her teeth cleaned on a visit but will need a filling? In other words, and this is where the notation comes in super important. If you just give me a number and it's wrong, you're out. There is no marks associated with it. If you give me the proper notation so you know what you're looking for and your calculation is wrong, you can still get marks. Okay? So the probability, what we're looking for is the probability of C dash intersecting with F. No cleaning but will need a filling. In this scenario, of course, I can identify that as whichever box that's meant to be in. Right, C dash is that second row here, and F is in this first column, so the answer would be 0.05. What is probability that she would need neither? Again, don't just write your answer down just in case, so that it's clear to the assessor. Probability of C dash intersecting with F dash would equal to 0.6, because that is neither. One page left. Alright, this next page is going to have a bunch of formulas for you, so please make sure you either highlight, circle, whatever it is, because I'm going to write a few myself as well. This first formula, I'm going to highlight it down. Please make sure you have it highlighted or written. And add to the side, assuming probability of B does not equal to 0. That's pretty straightforward. If the probability of B equals 0, that is an non-defined or undefined formula. Conditional probability we've done before. Please say yes. Conditional probability we've done. Okay, so just in case, as a quick revision, conditional probability is saying that let's find the probability of this given this, or on the condition that, etc. Okay, so it looks at one event A occurring when another event B has already occurred. We're assuming that. Okay, so the way we read it is A given B. Now the scenario might be different, of course, but the line means given that. Okay, so the probability of A given that B equals to the probability of A intersecting with B over the probability of B. In other words, we're saying let's look at this small sector. If we know one of them has happened, let's look at this small sector and find the probability of that event happening in that small sector. That's what that formula comes from. Okay, the formula can be rearranged to get the multiplication rule of this. It's really just an application. You don't have to memorize this one. You just remember the other one, and you can substitute and rearrange, etc. as you wish. Something I was mentioning earlier regarding the independence of events. If two events are independent, the probability of one event occurring is same regardless of the other one. It doesn't care about the other one. It's independent. Yeah. So there are 3 formulas associated with this, but they are very similar regardless. Please write them down. The first one is the probability of A given B equals to the probability of A. Because if B's happened, up the back. Abby, thank you. If B has happened, right, and we're looking for the probability of A when B has happened, but they're not related and they're independent, it doesn't matter. It's just going to be the probability of A. And inversely, of course, the probability of B given A equals to the probability of B. So those are very, very similar. The formula after that is one that you will have to memorize, unfortunately, though it might actually be on the formula sheet. I forget, but it's a very easy one to remember. The probability of A multiplied by the probability of B equals to the probability of A intersecting with B. It's an independent event. That's what we're used to. It won't always happen, but it's what we're used to. Okay? Happy to move on? Great. There is, you know what, I'm going to add one more formula. It's not related to interdependence. I just want to clarify that. I will write it at the top. It's called the law of total probability. You do not need to know the name. That is not relevant. What you do need to know is that the probability of A equals the probability of A given B multiplied by the probability of B. I'll explain this in a moment. I promise it's a lot easier to interpret than what it is right now. Plus the probability of A given not B times the probability of not B. Ooh, okay. Let's break it down. Pretty much all it's saying is that the law of total probability tells me this is true. But let's break it down. This section right here is just the rearranged version of the conditional probability formula. Yeah? If I multiply both sides and move this over here, I get the probability of A given B multiplied by probability of B equals to this. So I'm going to write that down here. The probability of A intersecting with B. Just to help clarify this, I am going to draw a Venn diagram. You do not need to copy this into your book. So let's pretend that's A, let's do that's B. Okay, so in this scenario, A intersect B would be this area right there. Makes sense. Let's continue. The other side of it is the probability of A given not B times by probability of not B. Same idea, except that's going to give us the probability of A intersecting with B dash. Or in other words, not B, which gives us this area. And alas, you'll see that is the same as just saying A. So that's where that formula comes from. The law of total probability. Any questions about that one? one example, then I'll let you get started. In a certain town, the probability that it rains on any Monday is 0.21. If it rains on Monday, then the probability that it rains on Tuesday is 0.83. You'll note it's not independent. If it does not rain on Monday, then the probability of rain on Tuesday is 0.3, etc., etc. In this scenario, by the way, I've just picked random numbers, they're not real, but in this scenario, it is a lot clearer to use a tree diagram for it. It makes sense. You've got this condition happening, if this happens, etc., etc. Please copy down the following diagram. Write it over here. Let M equal to Monday rain. And I'm going to write T equal to Tuesday rain. Yes, I'm very creative with my letters. Yes, go for it.
When you write M dash or dash of anything,
Mhm.
I assume that the condition does not happen?
Correct. Yeah. So in this case, M would be Monday raining, M dash would be Monday not raining. And then your outcomes afterwards would be T, M, or T given M happened, T dash given M happened, T given M dash happened, and T dash given M dash happened. I'm going to go ahead and label my probabilities. It says that the probability that it rains on any Monday is 0.21, so I'll label this as 0.21, and I'll fill in the gap for the one underneath. And of course, it makes sense, it either rains or doesn't rain, so it would be 0.79. If it rains on Monday, then the probability that it rains on Tuesday is 0.83. At last, that would be 0.83 as well. If it does not rain on if it does not rain on Monday, then the probability of rain on Tuesday is 0.3. This one will be 0.3. Again, I'll fill in my values. Of course, it needs to add up to 1, so that will be 0.17, and this one will be 0.7 as well. Great. On both Monday and Tuesday, if it's both Monday and Tuesday, we're going to look at this value right here. Of course, we're not just finding that, we're going to go multiply it out. So the probability of Monday intersecting with Tuesday equals, because we've got this one right here, right? We've also got this, sorry, we're following that path, aren't we? So it would be 0.2 multiplied by 0.83, 0.21, sorry, times by 0.83. Which if you put in the calculator will give you an approximate value of 0.1743. On Tuesday, the probability of raining on Tuesday would equal to the probability of Tuesday intersecting with Monday, which makes sense, but also plus the probability of Tuesday intersecting with not raining on Monday, which will give us an answer of, and I'm going to use the value from above, 0.1743 plus 0.237, and I'm getting that by multiplying out my Tuesday and not Monday, which would give me an answer of 0.4113. You can do example 6 in your time if you'd like. Yeah.
So did the 0.237 come from 0.3 times 0.7?
Yeah. Any questions? Great. I've